Hello everyone and welcome to this theory prep video. Today we'll be talking about functions and sizes of sets, which seems like an easy question at first, but will actually lead to a pretty cool case study on what makes a good definition. So let's get right into it. Let's first do some thought experiments and ask some questions just to capture our intuition so we can make a good definition of the size of a set. So how do we know for finite sets which set is larger? Well, if you have the set 1, 2, 3, we usually denote the cardinality or size of the set with these two bars, and this set has 3 elements, which cardinality is 3. This set has also 3 elements, and so we would say that the cardinalities are equal. Similarly, this set here has 3 elements, and this set here has 2 elements, so we'd say that the set 7, 8 has a smaller cardinality than the set 1, 2, 3. And maybe another way that we might be looking at this is, well, we know that 1, 2, 3, and 4, 5, 6 have the same number of elements because we can just pair them up, 1 to 4, 2 to 5, 3 to 6, and we use every element exactly once. So that might be another sort of like explanation where we could talk about that. So this leads to sort of a tentative definition of when a set is larger. So we'll say a set S is larger than a set T if S has more elements than T. So just count the number of elements in each set. Whichever one has more elements is the larger set. That makes a lot of sense intuitively. But we run into a little bit of an issue because what about infinite sets? So let's just consider the natural numbers and the integers since those are the ones that we've been working with the most. So again, to remind you, the natural numbers are the set 0, 1, 2, etc., etc. And the integers are the set 0, 1, 2, etc. And they also go down to the negative integers, -1, etc., etc., etc. And so we might be tempted to say, well, clearly the natural numbers are smaller than the integers here because every natural number is an integer, and the integers are, they contain all of the natural numbers and more, so they must be bigger. And so that would lead to sort of a definition that says a set S is larger than set T if T is a subset of S. That's what we're saying. We're saying the natural numbers are a subset of the integers and therefore they're smaller. But there's a number of problems with this definition as well. The first problem is, well, here we said 7, 8 was smaller than 1, 2, 3. I think that's pretty undisputed. But 7, 8 is certainly not a subset of 1, 2, 3. Another issue might be, what if we just represent the natural numbers as like 0, 1, 1, 0, 1, 1. They're binary representations. Then this definition now says the integers are not bigger than this set, but I think it's pretty intuitive that these two sets should probably have the same size since we just replaced every element with something else, so there should be the same number of elements in them. So this definition doesn't work there because it says that the integers are bigger than natural numbers, but the integers aren't bigger than this set that we think is the same size as the natural numbers. So lots and lots of issues with this definition. So we're going to have to reframe it again. And so in doing these thought experiments, I think we've realized that two sets, first of all, when we were looking at finite sets, two sets are the same size when we can sort of do this pairing of elements, right? And even with the natural numbers and the integers, what we were sort of trying to do was we want to make an argument where we were going to assign each of the natural numbers to one of the integers and then show that, oh, we run out of natural numbers first, right? So by sort of assigning elements in one set to the elements in another set, we can argue about how large or small they are. And I think this is the right idea. So we're going to formalize this notion of assignment, though, through functions. So a total function f from some set A to some set B, which we write as f colon A arrow B, assigns each element of A to exactly one element of B. So this is exactly what we've been doing, right? We've been taking every element in the natural numbers or every element in one set and assigning it to exactly one element in the other set. Based on, like, do we have leftover elements? Do we have too many elements? We've been trying to argue, oh, this set is larger or that set is larger. And so functions really capture this notion mathematically. And so we'll try and use them to define sizes of sets. One advantage of functions is that they work over infinite sets. For example, you guys have seen lots of functions. A function might be f of x equals x plus 2. And this is a function from the integers to the integers. And so unlike our naive definition, which is count the number of elements, this definition will actually work over infinite sets, which is exactly what we're trying to do. We're trying to get a definition that works for infinite sets, but still really captures the same intuition that we have for the finite case. Great. So Next thing that we have to do is we need to see what properties of functions indicate like when a set is larger or when a set is smaller. So let's start with larger. And a good place to start is in the finite case, what do we mean when we say A is bigger than B? So I've given a set here. The first set we'll call A, and the second set we'll call B. And what we mean here when we say A is bigger than B is that we can, if we send each element, if we associate each element of A with an element of B, we can cover all the elements in B. And that means that A must have at least as many elements in B, right? Because you can cover all the elements of B with the elements in A. And mathematically, we say this function is a surjection. So a function from some set A to B is surjective if for any B in little b in big B, so for any element in the range, there exists an A, so there exists an element in the domain such that that element maps to little b. So what we're saying is, that's mathematically formalizing the notion of covering, because what we're saying is anything in the range, any number you want to pick in the range or any entity you want to pick in the output set, well, here's something in the domain that goes to it. So we're covering that. And since that's true for all the elements, we're covering everything. And so we'll say if a surjection exists from A to B, then we say that the cardinality of A is greater than or equal to the cardinality of B. And the one important thing to observe in this definition is all that we require is that a surjection exists, not that every function between the two sets is a surjection. Because, for example, consider this A and this B here. Clearly A is greater than B, but if we take a function that just trivially maps everything in A to 4, then it's not a surjection. So just because a set is bigger doesn't mean that every function will be a surjection. It just means that there exists a surjection. And so let's just make sure, we're inspired by finite sets. Let's make sure that for a finite set, this definition makes sense. So let's say, let's define some new set A with some arbitrary number of elements. We'll say it has n elements, say 1 through an. And then we'll define some set B, and it'll have elements B1 through Bm. And I claim that, let's say that n is greater than or equal to m. So in the finite case, that's what it means for A to have, right? That captures our intuition for A being larger. Well, if n is greater than m, then we can rewrite this first set as A1 through Am, and then Am plus 1 all the way to An. And now we can define our function as A1 maps to B1, A2 maps to B2, et cetera, all the way to Am maps to Bm. And if there are these elements, right, if like n is strictly larger than m, then we'll just map all the rest of this stuff to Bm. And clearly this is a surjection. So our definition works in the finite case. And now let's take a look at what it means for a set to be smaller. So again, taking intuition from the finite case, let's look at A and B, and in this case, A is smaller than B. And one way we can explain why A is smaller than B is if you match up every element of A into an element of B, we can give each element of A unique element in B, and that implies that B has at least as many elements as A does. And so we capture this definition mathematically by saying that a function f from A to B is injective if for any two different elements in the domain, they map to different elements in the range. And that's what we're saying here, right? We're saying B has at least as many elements as A because you can assign every element of A to a unique element of B. And similarly to sort of the proof that we did of surjectivity, where we enumerated out the elements, you can do a similar proof to show that in the finite case, if you have a smaller set and a larger set, well, there's always an injection from the smaller set to the larger set. So indeed, it does sort of capture that relationship. Now, we should try and check for a property that mathematicians would call well-definedness, right? So on the last slide, we talked about what it meant for one set to be larger than another. In particular, we said if there's a surjection from A to B, then the cardinality of A is greater than or equal to the cardinality of B, right? That's how we defined it. And our conversations about injectivity here would lead us to make a similar statement that if there's an injection from A to B, then the cardinality of A is less than or equal to the cardinality of B. And when mathematicians say well-definedness, they mean that like if you had two different ways of defining something, that they would lead you to the same conclusions. And we'll see that this is actually true, because in this course we'll assume something called the axiom of choice. You don't necessarily have to worry about exactly what that means, but basically one of the implications is that if you have an injection from A to B, well then there's a surjection from B to A, and then so by definition that implies that the cardinality of B is greater than or equal to the cardinality of A. So we see that we have the well-defined property here. Like if you use either of these two definitions, you would end up with the same thing. The last thing that we want to do is talk about what does it mean for sets to be the same size. And as we were just discussing, definition should follow our intuition, right? And so far, we've said that if there is an injection, that if there's an injection from A to B, that means that A is weakly smaller than B. And we've said if there's a surjection from A to B, then A is weakly bigger than B. So that means that sort of suggests that if we have some function that's both injective and surjective from A to B, then that would imply both of these are true. And so then we would expect the cardinalities of A and B to be equal. So that's what our definition will be. We'll just say if a function is bijective, if it's both injective and surjective, and then we'll say if a bijection exists between two sets, it means that they have the same cardinality. So let's check to make sure that holds up again in the finite case. So let's say we have some set A with n elements, A1 through AN. And let's say we have some B with B1 through Bn. They have the same number of elements because that's what it means to have the same cardinality in the finite case. And now we could just define a bijection, again, A1 to B1, A2 to B2, all the way through AN to Bn. And clearly a surjection since it hits everything in B, and it's also an injection since every ith element of A is being mapped to the ith element of B, so they're all being mapped to different things. So again, it matches our intuition in the finite case, which is exactly what we would want it to do, but now we have a more powerful definition because it also works in the infinite case. So let's give an example in the infinite case, because if we're not going to use infinite cases, then there was no use in extending this definition and building all this mechanics. And what I'm going to show is that the natural numbers have the same cardinality as the integers, which, at least when I heard it the first time, was a really surprising result that I didn't expect. And remember, by our definition, if I want to prove that these are the same cardinality, I must show that there is an injection, some f, I must show that there's a bijection, some f, that maps from the natural numbers to the integers. And I've given a candidate bijection below. So I'm going to show that this f is both surjective and injective, which implies that the cardinalities are the same. But first, let me just draw a little picture because I think this will help. So let's list out some of the natural numbers, 0, 1, 2, 3, 4, and then let's list out some of the integers, 0, 1, 2, -1, -2. Okay, so if we take 0 and we put into f, 0 is even, 0 divided by 2 still gives us 0. Then if we take 1, 1 is odd, so we add 1 to it, we get 2, divide by 2, get 1, put a negative in front, that'll give us -1. 2, even, divide by 2, gives us 1. 3, add 1, 4, divide by 2, 2, put a negative in front, gives -2. 4, divide by 2, gives us 2. So what you're seeing here is basically, we've taken all the even natural numbers and we've mapped them into the positive integers. And then we've taken all the odd natural numbers and we've mapped them into the negative integers. And so we're covering all the ground on the integers by just like ripping the natural numbers in half. So that's sort of the intuition behind the construction. But now, so first, we're going to prove that f is surjective. Mathematically, what we need to prove is that for any integer, there exists a natural number such that f maps that natural number to z. And we're going to do this in cases. First, let's consider z equals 0. Well, in that case, we already know that f of 0 equals 0, and 0 is a natural number, so this checks out. The next case we'll consider is z is greater than 0. In this case, I claim that f of 2z will give us z. Let's check a couple of things. First, we should check that 2z is an actual natural number, because f is only defined on the natural numbers. And in fact, if z is greater than 0, then 2z is a natural number. The second important thing is that 2z is actually even, because it's 2 times some integer. That's the definition of being even. And so therefore, we're in the first case, and f of 2z just gives us 2z over 2, which gives us z. Now, remember to make sure that your cases are mutually are exhaustive. And so here, last case we have to check is that z is less than 0. And in this case, I claim that f of negative 2z minus 1 will give us z. Let's check this. First, again, we need to check that this thing that we're evaluating f on is a natural number. And indeed it is, because if z is less than 0 and z is an integer, well then z is less than or equal to negative 1, which means that if you take something that's less than or equal to negative 1 and you multiply it by negative 2, you'll get something that's greater than or equal to 2. And so we have something that's greater than or equal to 2. We're subtracting 1. That means that we're still greater than or equal to 1, which means we still have a natural number. The second thing that you should observe is that this quantity will also be odd, and therefore we'll apply this second part of the definition of f. So if we evaluate this, we'll get negative of negative 2z minus 1 plus 1 over 2. The 1's cancel, the 2's cancel, the negatives cancel, and we'll end up again with z. And so we see that in all of these cases, we're able to find a natural number that maps to that integer, and therefore f is surjective. Proves it's surjective. Now let's prove it's injective. And remember, in order to prove that it's injective, we must prove for any 2 natural numbers, n and n prime, that are not equal to each other, that the function evaluated on n is not equal to the function evaluated on n prime. So suppose, towards a contradiction, that there exists some n and n prime such that n is not equal to n prime, and they evaluate to the same thing, right? So suppose we basically have like a clash. We have 2 things that map to the same number. Well then, first, we know that n and n prime cannot be, like one of them can't be even and the other one is odd, because the even numbers map to the non-negative integers and the odd numbers map to the negative integers. So if one is even and one is odd, they clearly cannot come out to the same thing. So we only have to consider 2 cases. So in case 1, we consider both even. In that case, by the second equation, we can rewrite it as n over 2 equals n prime over 2, because by the definition, we send n to n over 2 since it's even. But that implies that n equals n prime, which contradicts our initial statement, our initial assumption, that n is not equal to n prime. So therefore, that can't happen. So let's check the other case. The other case is that they're both odd, and this is very similar. Again, by the definition of the function, we can replace f of n with negative n plus 1 over 2, and we can replace f of n prime as negative n prime plus 1 over 2. And that again implies that n equals n prime, which is a contradiction. So therefore, we've reached a contradiction in both cases. We see this can't be possible, and therefore the function is injective. So the function is therefore both injective and surjective, and that proves that it's a bijection. So that implies that the natural numbers have the same cardinality as the integers under our new definition. And you might think, I don't understand this. This doesn't make sense to me, because literally the natural numbers are a subset of the integers. How can they possibly have the same cardinality? And I think there's a couple important things to keep in mind. One is that the definition of the definition of cardinality for infinite sets is not something that's immediately intuitive. Like with finite sets, you can't add or subtract an element. If you add or subtract an element, you'll change the cardinality. But with infinite sets, you can do lots of things. You can add an element, subtract an element, it'll still stay the same cardinality. In fact, in this case, we're basically doubling, like quote unquote, doubling the number of elements, right? But it still has the same cardinality. I think the easiest way to think about this is, what does this bijection f mean? This bijection f means that we could replace every single element, n, in the natural numbers. We could replace each of them with f of n. And then the resulting set would literally be the integers, right? That's what it means for this bijection to exist. If we replaced each of the natural numbers with their image under the function f, we would get the integers. So it would actually be weird if we didn't say that these were the same size, because we could just replace all the elements with different elements and get the integers, so they must be the same size. Because if you replace all the elements, that can't change the cardinality of a set. So hopefully that gives a little bit more intuition for what the answer to that is.